in this lesson we discuss the direct sequence spread spectrum technique, and this is one of the most popular modulation and transmission method that is used in wireless communication. It is commonly known as DSSS, and it uses the spread spectrum that we have already introduced, the concept of spread spectrum, and we have already seen the spread spectrum increases the bandwidth of, if this is our narrowband signal, the spread spectrum kind of transforms this one to become a wideband baseband signal. So we call this one wideband baseband signal. So as you can see on the frequency spectrum or frequency axis, if this is F and this is power spectral density of our signal, we see that we are able to reduce the power spectral density of our narrowband signal, and therefore this one will not be detected by an intruder or a jammer. And we do this by introducing a very high bitrate PN sequence, like we have already talked about PN sequence in our previous lecture, which we defined as pseudo random noise signal. And one of the reasons why we normally spread our narrowband signal to become wideband signal is that in narrowband wireless communications, more power is required to overcome jamming and interference. So if we received another signal here that we can call a jamming signal, the signal to jamming noise ratio that is required so that we can detect this signal is very high. But after we spread the signal, our signal takes much bandwidth but appears with very small power spectral density, as you can see in this signal. And this signal in itself appears like noise, and therefore becomes almost difficult for anyone to determine whether a signal is actually sent or not. So we say that the noise-like signals are very hard to detect or interfered with, and this becomes the benefits of DSSS. And they are very much used today in wireless communication and even in military applications. That serves to introduce the DSSS. And now we talk about the definition. And we define the DSSS as simply a high-speed pseudo-random noise code that is employed with raw speed data before or when it is being sent. That allows us. So the keywords we are underlying here is that we have a high-speed pseudo-random noise code that is employed to send low-speed data. And we have already seen that this information is multiplied, and what we will see in our subsequent slides, when we say multiplied, we might mean different things. Sometimes we are going to do XOR operation, in which case we call this one modulo 2 summation, or we might use an add operation where we just check if we have 1 and 1, what do we get? We get a 1. So we will look at those one in subsequent slides. So we say that this method results in what is considered to be a high bandwidth signal that is transmitted, and as we have also seen, the power spectral density is reduced, and our signal that we are sending appears like we are sending noise. I'm just kind of reviewing what we have already seen. When we have sent this kind of signal that is spread, we need to be able to recover our original signal that was having this bandwidth. So what we do is we use a discrediting code that is identical to the one that we used to send, and we see the mathematical rigor that shows that to be true. So we say that most particle systems that employ DSSS employ additional modulation scheme that we have already learned for it to be sent over the wireless channel over a long distance. So we don't use the DSSS alone. Most of the times we combine it with digital modulation scheme like BPSK or QPSK to transmit our data over a long distance. So we'll now look at the signal space representation of that kind of transmission. We have already made this diagram before, but we never talked about how mathematically they are related. So we have here our digital line code that is expressed as DT, and we have our pseudo random noise code that is expressed as CT. This is the one that now will generate our DSSS signal that we will now refer to as MT, and that MT is the one that we use to modulate our carrier signal, like we have seen before, cos omega CT, so that it can be used to transmit long distance to produce ST. And now we are saying that in long distance, or through this wireless channel that you are transmitting, we will consider that we do not have noise that is significant. The most troublesome issue that we are going to be dealing with is the interference. So as we have already seen, the operation that we are performing here may be XOR or may be AND, and we have said that this one is often called modulo 2 summation. And we have said that in this channel, we are saying that this noise is considered insignificant. So now we want to see the model representation of this information and mathematically show how we are able to transmit our message signal dt, and we are able to recover dt on this other side. Even though it has passed through an interferer jt, what happens? So we'll do that very briefly. So we have seen that our message signal is dt, and dt is multiplied with our PN sequence that we have symbolized as CT, and this now becomes our MT. So if for the time being we ignore the bit where we are doing the BPSK modulation and we only deal with the DSS modulation, we want to see how we are able to recover our DT at the end of the demodulator. So assuming we are setting the MT, this is the easy part, because even if we do not ignore the BPSK bit, we are saying that MT, when it goes through the BPSK modulator, will be multiplied with high frequency carrier called omega C of T, and this is what we receive at the receiver. This is what is transmitted through the channel. So at the receiver, we employ the coherent detection that has a local carrier with a signal that is synchronized with the one that was used at the transmitter. Therefore, we multiply again with the cos omega CT, and we have already seen the mathematical figure that shows that we are able to get our MT back. So that is the bit I am saying that we can ignore. This is now what we are going to have received on our RX side. We have seen that when you do BPSK modulation, you are able to get your MT back. Now, assuming we have MT, but now this MT, and it was being sent through the channel. This is the MT that we sent here. But along the channel, we have interference J of T. That is what we have seen. So what we want to find out, how are we going to be able to recover our MT now in the presence of interference JT? At this point, we have said we have ignored the concept of noise, and we are saying that the channel is only interference limited. And therefore, the question is, how are we going to be able to recover? Because what we are receiving at this side as RT is equals to MT plus JT. So what we will see very simply is that we have said that we are going to be having on, this is the one that we are saying that we have already taken care of because it has done the demodulation. So this bit we are saying that it is quite clear. The only thing is that when we have sent MT here, our U of T, or the one I'm called RT, is equals to M of T plus J of T. So we want to find out how are you going to recover this one. And we are seeing here is that we are doing another multiplication with our local PN code CT. So that is what we will do in our here. Now we are going to multiply U of T. It is multiplied with another C of T. What are you going to have? So we say that our U of T is M of T plus J of T, and this is now multiplied with C of T. But you already know that M of T is equals to D of T times C of T. So we can do that. D of T times C of T times C of T again. So it becomes C of T squared plus J of T times C of T. This is what we receive on this other side as U of T. And what we have seen before is that this C of T squared is what we call the autocorrelation function of our PN code. And when we evaluated the autocorrelation function of our PN code, we found that it is equals to, remember we said something like, that time we are calling it P of T. And we said P squared of T is equals to 1 only when the delay tau is equals to 0 or tau is equals to n. So we can conclusively say that this autocorrelation function will give us a 1. And therefore, when we have a 1, this becomes a 1, and therefore we are left with, on the receiver side, we are left with D of T plus J of T multiplied with C of T. And now it appears like at the modulator side, we have now spread the interference and we have got our message back. So if you are to draw it on the power spectral density diagram, where this is F and this is our PSD, we'd actually be able to see that we have our signal with frequency similar to the one we had sent earlier, which is FB, or the bandwidth, but now our gamma has been spread. This is now the one we are calling J of T multiplied with C of T. And therefore, the power spectral density of our interference is very small. And therefore, we just apply a filter. We'll just apply a filter that will cut off this entire noise. And you're going to be left with only a section of bandwidth range of that of our original transmitted signal dt, and therefore the noise is cut out because it has power spectral density way less than that of the signal. Then it will not have much effect on our received signal.